Okay. Hello, everyone, and welcome.
Welcome, Jeff. Welcome, everybody. My name is Wiebke. I'm the marketing director at we.CONECT Global Leaders, and it's my pleasure to welcome you to today's webcast with Altia. Before we start, just a short briefing for you. First, within the webcast will be a live poll, so you can tick your answer in the pop-up. And second, all attendees are muted. So if you have any questions, please use the Q&A button. Jeff will answer all questions coming in the Q&A sessions in the end of the webcast. So that's all from my side. Enjoy the webcast, and Jeff, you can go ahead and start.
Sounds great. Thank you, Wiebke. So my name is Jeff Stewart, and I'm the Director of Field Application Engineering at Altia. Today, we're going to take a look at the embedded system market growth, and specifically, we'll look at the growth within some of the segments in the embedded system market. We'll look at how increasing software complexity as that software grows presents a problem for development teams. We'll take a look at why the traditional development process contributes to those issues, and how if you can adopt a low-code, no-code solution, you can increase the efficiency and optimize your team's output. The embedded system market continues to expand, with projected growth from 2020 to 2025 moving from 86.5 billion to 116.2 billion. That's about a 6% compound annual growth rate. Embedded software contributes to this growth, growing from 12 billion to 20 billion over the same period of time in a variety of sectors. Automotive is definitely one of the big drivers of this growth. Between electrification and autonomous features coming into the vehicles, not to mention the user wants to bring their digital ecosystem to the car with them. All of this is driving more software into the cockpit of the vehicle and other systems in the vehicle. And it is also increasing the amount of data that must be displayed to the driver and passengers of the vehicle. Following the lead of automotive, agriculture is putting more sensors and software into their machines, allowing the users to see precise locations and operation of the equipment, and therefore optimizing the results. Many other industries that didn't have really any software in them previously are now adopting more software and displays to get better information to their users. Recreational vehicles and motorcycles are increasingly adopting digital instrument clusters, and construction equipment are adopting digital displays to show the status of the equipment and its operation. So while all of that growth in software is very exciting, especially to the end users about what you can do with your equipment, there is a bit of a problem reported by the McKinsey & Company, where they're noting that the software complexity is growing much faster than the average team's software development productivity. And this poses a bit of a problem that embedded and GUI engineers must produce more capability in less time than they ever have before. The challenges for the embedded and GUI engineers are increased in the integrated cockpit environment in an automobile, where many different factors need to come into play. For example, you have cybersecurity, where you have to worry about unauthorized actors working on the vehicle. You have connectivity to allow connection to the 4G and 5G networks outside the vehicle. Of course, in any vehicle, safety is paramount. So you have to maintain government safety standards like NHTSA and also ISO 26262 requirements. The users want third-party apps in the cockpit so they can bring their digital ecosystem and social media and things with them to the car. And then, of course, that means that these systems must run on multiple operating systems throughout the vehicle, because you have some that are more hardened embedded RTOS systems like a QNX, and then you have others that are connected high functionality operating systems like Android. If we take a look at the traditional development method, it's a bit of a fractured process. You have designers who build the look and feel of your devices. You might have systems engineers who are developing the behavior of the device and specifying requirements for how the device should be built. Then you may have quality managers who are specifying certain quality standards that the products may live up to, like ISO 26262, and then also specifying quality processes that must be followed during the development. All of these things end up being input to the software development process, meaning that that traditional development process ends up being a very serialized process. Most of these other departments need to be complete or nearly complete before the software development can even start. That means the process is slowed down, potentially limiting the amount of total time that the software development has in the project cycle. If we take a look at the traditional development method, specifically in the integrated cockpit environment for automotive, you could see that, again, we have the UX and design team, the system engineering team, and the quality engineering team up here, and they all have to provide output to what end up being multiple different software development teams down on the lower part that all have to get their software to run on the same chip. So in this case, the UX designers have actually 3 different places they need to output graphical assets to. Some teams might be developing in Java or Android for the more connected features. There may be teams developing in C++ for some of the vehicle specific IVI or maybe less connected features app level. And then you have other development teams that are probably developing more low-level things in C, connecting the hypervisors to the different operating systems and making sure that integrates properly, and also building in the ISO 26262 solutions that may be required in the system. Having all of these teams only compounds the serial part of the process, meaning that you have all of the behavioral specifications and those teams coming from design and systems engineers and quality going to your Java team, and then to your C++ team, to your C team. Those all have to come together because each one of those teams will need to be a certain degree complete before you can actually integrate to the board and try the product out running all together. So it poses a bit of a paradox, because embedded software and GUI engineers are some of the most difficult to find in the workforce, but they are being given more tasks unrelated to their specialties in the field, which effectively dilutes their efficacy. And it means that they have to get involved with things like safety issues, design issues, things like this that are not necessarily embedded software or GUI related. The solution to this is if you can share the load across the team and decrease the code that the team has to manually create. By getting smarter about the tools used by the development teams, companies can avoid putting such loads on the software and GUI teams, and instead they can increase productivity and quality simultaneously. Model-based development tools are key technology to enable this efficiency gain. Altia builds a number of model-based tools for HMI development Starting with Altia Design for building a design and modeling your HMI on the PC environment, Deep Screen will then automatically generate code for that, and then the Altia test solutions help you test your design. Similarly, on the logic side, tools like LabVIEW from National Instruments and Simulink from the MathWorks allow you to model the behavior of your system. This allows engineers that may not be familiar with writing code the ability to still contribute to the actual implementation and modeling of the behavior of the device, meaning that the load can be distributed such that your designers may be building up some of the model in Altia. Your systems engineers can be building up your logic models in MATLAB and Simulink, for example. And then your embedded engineers are really focused on integrating the auto-generated code from both of those tools onto the board, which is what the embedded engineer's expertise is really. Of course, there are tools like IBM's Rhapsody as well, which allow you to model the structure of your code and then once again, auto-generate the code for your platform. So we come to our first survey question where you all get to participate. And the first question is, have you ever, or do you plan to use a model-based development or low-code, no-code solution for GUI development? You should see the questions pop up and you're able to click on the answers. If you would please click on those and submit those, and then we'll all get to see the results and we can discuss that a little bit. Please be sure to go ahead and submit those. The answers are anonymous. It's just going to give us kind of percentages so that way we can kind of see across the audience, you know, who does and who doesn't use these. It's kind of interesting to look around. Good. So based on the survey results, it looks like we have quite a few of you that do use or plan to use. 88% say they do or plan to use the model-based development or low-code, no-code solutions. And the other 13 are really in the don't know category. Nobody's saying that no way they're not going to use that. So that's great. So we'll move on. Thank you for participating in the surveys, by the way. So let's take a look at, if you did adopt model-based design, how that low-code, no-code workflow works in the same integrated cockpit environment for automotive. In this case, instead of having the discipline teams, say design and systems engineering and so forth at the top, those teams are actually participating, as we talked about in the previous slide, in the development of the actual model of the system. So therefore, you have your designers participating in the development of the HMI models for your cluster, for your IVI, and for your rear seat entertainment. Those designers can be using whatever design tools they like, as well as Altia Design to generate that model. At the same time, the systems engineers and possibly some of the quality managers and so forth can be building the behavior model in MATLAB and Simulink, and they can be modeling those together with the HMI, all in the PC environment. That really allows each team to fully test their unit and can allow all of the teams to simulate these various pieces of the integrated cockpit together in the PC environment before they even worry about what hardware or anything that's going to run on. Next, they go to automatically generate code from the models that they've built. And that automatic code generation can target the various operating systems that are required. For example, your cluster and HUD model may want to run on a more hardened RTOS like QNX or Green Hills, whereas your IVI and rear seat entertainment models might have interactions that are more appropriate for connected operating systems like Android or iOS. The model-based and automatic code generation really doesn't care where it deploys. It just needs to know what it's deploying to and is capable of deploying to that platform. This frees up your embedded software engineers to really focus on what they do best, which is making sure that these RTOSs and operating systems are running properly on the hypervisor in the CPU. They're also doing some of the low-level C coding that may provide drivers or other communication methods to other parts of the vehicle, like the CAN bus or so forth. And in addition, they can focus on making sure that some parts of the code are compliant to ISO 26262 and other government mandates to make sure the safety goals and things are met. Another advantage this has is that all of the code development is done the same way automatically. And if you want third-party apps that are, say, Java, those can be done completely removed from the overall development process. All of the base logic of the vehicle functionality and things are modeled in the same tooling at the top here. So really the other development methods are for other apps. That means that you could have specific teams doing apps if you like, or you can even just rely on outside sources to develop and provide apps for you. So it brings us to our second survey question, which is, where do your GUI concepts start when you go to build an HMI? So with those GUI concepts, it basically looking for what types of tools do you use to generate your look and feel assets and bring those into your actual implementation. And a UI mockup tool might be tools like Axure or things like that that allow you to wireframe. And then of course, 3D video software might be like After Effects or Maya, things like that. Great, looks like we're getting some results here, so that's great. Alrighty, so the GUI concepts start overwhelmingly in PowerPoint. So 60% of you said that your GUI designs will start in PowerPoint. Another 47% said that they'll start in drawings. The next highest is a mock-up tool, so something like Axure, maybe Figma, things like this. Next one down is Photoshop at 33%, Excel at 20%, and 3D and video software making up only 7%. So thank you guys. It looks like many of you are using kind of a PowerPoint and drawing method, which is extraordinarily common and a good way to communicate those things. And a model-based environment, creating a model may help you make that fairly efficient. All right, so we'll move on. So we'll look into a little bit more about how development in a model-based environment of your GUI can look using Altia's software. You can start with the assets that you've already developed in drawings or Photoshop or XML, 3D graphics. You can even pull in graphics from PowerPoint if you like, and you can bring those into Altia Design. In Altia Design, your graphic designers can help build the HMI up. They can add touch interactivity to it. And then they can also provide the names and things to connect to the behavioral control logic that you might be simulating, for example, in Simulink. Of course, you can also add things to specify certain objects as safe objects and to be used with Altia's safety monitor, which is the ISO 26262 solution. And then, of course, you can provide do some HMI testing using the Altia test solution to make sure that your HMI is coming out correctly. Once you do have simulations correct using Altia Design and your Simulink logic, you can then use Deep Screen to generate code for your HMI. That can be put together with the generated code from your Simulink logic, and then that's ready for production. That is C code that is developed to MISRA requirements, and it's ready to go into your vehicle. If we look at a little more detail about why this process can be such an efficiency gain and such a savings for your team, we can look at the standard software V chart. So the start of the V chart is very much the same in a model-based or other development paradigm, where you start with specification and then some sort of model or prototype or something of the tool. In a model-based paradigm, you can use a tool like Altia Design or Simulink to do this specification documentation, which normally might be written in a document or a PowerPoint presentation. It can actually be documented by the modeling tool. Also, it is modeled by the modeling tool such that you end up with a functional specification. So you no longer need prototypes or things like this to communicate the specification to other members of the team. The next steps are where the largest savings in the model-based development come in. And that is that once you have the model, the software development part is done for you because the software is automatically generated. So in the case of your HMI, Deep Screen will generate C code for the Altia Design. So it knows how to design and implement that C code. And then that C code is debugged and verified in Altia's side as we build the Deep Screen product, and similarly in other model-based tools side, as they verify that the product develops the proper code for the model that you've built. So that's done for you already, meaning that this whole bottom part of the V chart is essentially automated for you. That means that you no longer have to follow the V chart all the way down and back up. You can actually start back up the other side right here, saving you this area under the curve in time and cost on your program. Of course, you do still have to validate that once you've built this model and implement it to the code on the hardware, you do need to test that. And of course, Altia has some tools with the testing solution that can help you test that. And Simulink has tools, and there are many other testing solutions out there to help you validate that what you've built matches your specifications. So you still have to do the other side of the V chart all the way up, but the entire bottom section is saved for you. If we take a look at a integrated cockpit environment, and then we can take a look at what types of tools might be used to develop each feature in it and how they might work together. We can use this example, which is from CES. And basically for the cluster, you can use Altia for your HMI design and Simulink for your logic. It might have a safety monitor because the cluster probably has some ISO 26262 requirements. And then it runs on a probably RTOS environment rather than a connected operating system. If we move to the center stack, that has a mixture of vehicle specific information, say in the HVAC, and more entertainment content, say in the media player down here. Therefore, you could still use Altia for your HMI design and Simulink for the overall logic of the system. But you may deploy the media player, for example, to an Android or iOS type of system so that you can take advantage of the connectivity and the access to other media sources, while you may keep your vehicle specific branded look and feel closer to you and run it on an RTOS that is not connected and is maybe potentially a higher level of cybersecurity. Of course, then on the passenger entertainment display, you can use Altia and Simulink to build your user interface and your logic. And you may be using a connected OS like Android or iOS for the mapping and things like that. Whereas you may also have some RTOS features to take advantage of either vehicle branded things, like tire pressure, or possibly even more critical things like certain functionality switches like lights, for example, and things that you wouldn't necessarily want run with a connected operating system. So by using this model-based design, you can see that you're basically designing your HMI and logic in the same way, regardless of your platform or its content. And you can still take advantage of what the connected operating systems bring to the table in terms of functionality for connectivity, for third-party apps, etc. But you can also maintain safe parts of the system by deploying some parts of the system back to an RTOS. Just as an example of how this looks in tools, here's an example of that center stack where we have a Simulink model that is running the logic for the interaction with that HMI. And then in Altia design, we have that HMI built. What can happen is you can actually run this Simulink model. And as you run this Simulink model, you can interact with the design in simulation, and you can see the data flow through the Simulink model, and you can even see what states it's in state machines, for example. At the same time, you can use Altia design to see what data is coming in and out of the HMI from the logic model. And you can also make sure that the animations look and feel correct and respond appropriately to the user's interface. So this brings us to our third survey question, which is, how do you convert your GUI to final implementation? And some of that might be if you do use PowerPoint or mockup tools or things like this, there's the logic transfer saying that somehow you've modeled the logic in one of the wireframing tools or something, and that transfers, but you have to manually redo the graphics, or graphics transfer is the other way, where maybe your tool allows you to automatically bring the graphics into your implementation, but you have to then recode all of the logic around it. Looks like we got some results coming in. Great. Okay, so this is good. looking at the results, it looks like most 69% have the ability to somehow transfer the graphics from the design tools into their implementation. However, following that, 46% say they really have to hand code the graphics into their implementation. 23% use an automated process to do that. 15% have, a tool where their logic transfers over into the implementation, but they'll have to implement the graphics themselves. And then 8% really have no connection between the two, and it's all manual. Good, so there's still a fair amount of graphics transfer, but not a lot of logic transfer, a fair amount of hand coding. All right, we'll move on. And the next couple slides talk about the benefits of adopting this low code, no code approach in your development. And the first big benefit for the development team is that you can engage the entire team in the development process. So as we talked about, now you can have your design engineers helping to build the models. You can have systems engineers helping to build the behavior implementations. So it's no longer a piece of paper that just gets kicked over to the software engineering team for implementation. There's actually implementation being built right from the beginning of the concept. This eliminates the needs for extra mockups and prototypes because as each team is building up the model is the mockup and prototype. Usually prototypes and mockups are used to communicate from one team to another. This is how the thing is supposed to work. But if you build a functional specification, you've already built basically a mockup as well as the specification together. This is one of the big powers of model-based design. That extra team support removes the burden from the embedded software resources, which really allows them to focus on how the hardware and software and things interact, which is really their deep expertise. And it keeps them from having to deal with as much of graphics and possibly other behavioral requirements that are less their expertise and more the expertise of the other individuals participating in the development. Finally, you can deploy your system with model-based design to an Android or an iOS connected operating system to take advantage of the services those provide. But you can also simultaneously deploy to an RTOS environment for mandated and functional safety requirements, meaning that you can still have the same high-level development process regardless of the hardware and software environment that you're deploying to. These development benefits also lead to business benefits for the same teams. So the same design and development paradigm that we just talked about for all OS and hardware configurations means that you have your team that's much more efficient. It can be a smaller team because they all know how to do those things. And there's only one way of doing it. There's not 3 different tools they have to learn and 3 different environments they have to program in or design in. And so that means less training overall for your team and fewer tool costs. Of course, that reduces your overall development cost because of the team's higher efficiency and these eliminated unnecessary steps. How many times have you seen something like a Flash or an Axure model that looks great on the PC and shows how the thing should work, but then it's basically left to collect dust once you go to production because you have to move that from that tool to something that's ready to go to production. Faster time to market, the whole team is contributing to your development. So again, we've removed that serialization of the process that we discussed where, certain teams like the design team and the systems engineering team had to be complete before they could bring that to market. Now the whole team is contributing all at once in parallel. It just speeds the development. Not to mention the early feedback you get from the modeling allows you to tweak and make changes before you get to the more expensive deployment to hardware and things like that. In the end, it leads to a higher product quality and higher market penetration because as you build a product that works great and looks great, it will also sell great. So that's the end of the presentation here, and we do have a question and answer session following this. So we'll go ahead and open it up to questions and go from there. Thank you.
Can you hear me now?
I can hear you now. Yeah.
No, sorry. Yeah. Okay, perfect. So thank you for your presentation, Jeff. We had some questions coming in, so I would start right away with the first one, if it's right for you.
Okay, sounds great.
So the first question I've got for you, given that recent chip shortages at pushing companies to change hardware mid-program, is the low-code, no-code approach still helpful?
Yes, in fact, as we discussed, that the low code and no code approach allows you to easily and seamlessly move between hardware and OS environments. So if you are developing in that approach, it's much easier for you to potentially change to a new hardware that is more available in the supply chain than the one that you initially started development on, or perhaps you can deploy to multiple different hardware types to reduce the strain on any one particular hardware component.
Okay, thank you. So yeah, next question. I just go it through, right? So for everything's coming in. So
sounds good.
Perfect. Second question. If I am doing an integrated cockpit with Android, how do I do model-based development with Android Studio?
Yeah, that's a good question. And that's sort of one of the limitations of when you have to bring in and mix these connected environments like Android, and you have to connect them to maybe less connected operating systems, you know, something like a QNX or something that's hardened. You typically, in the traditional methods, you have to use Android Studio to build for your Android system, and you have to use you know, something else to build for your QNX system, because Android Studio doesn't do both and many tools don't do both. However, if you adopt this model-based design with Altia and Simulink, you can actually use the same design flow on your Android system. So yes, you're not using Android Studio anymore, but you're able to use the same Altia design and Simulink flow that you use for your QNX environment on your Android environment, and you use them the same way. So it allows your team to deploy to Android without having to use Android Studio.
Thank you for explaining, Jeff. The next question I have on the plate is, if I use this approach and still need to target multiple operating systems, how am I saving my embedded engineers time?
Yeah, good. So as you target multiple operating systems, if we looked at the traditional method, each of those operating systems would probably require a certain tool chain. And in fact, just like we talked about here with Android, if you had an operating system that's, you know, maybe Android that's Java based, you might have this team that has to use Android Studio and Java to develop for that. You might have another team that has to do C++ on Linux for some other components. And then you have another team that's doing C with an embedded RTOS for the cluster. And all of those are different teams. Whereas if you can adopt this model-based design, the code generation tools will automatically take into account the different pieces of hardware for you, such that you can use the same design methodology across the different hardware platforms, allowing the same team to deploy to multiple hardware platforms and OS platforms without having to be as concerned about the differences in those. At the low levels, your embedded engineers will be focused on how those operating systems interact with the hypervisors, for example. But that's a lot smaller task than having to completely build different software for each hardware and OS environment.
Mm-hmm. Oh, thank you. This leads me to the next question regarding the team you just mentioned. So how does the team size impact the benefit of the low code, no code?
So one of the benefits of the low code, no code is that you can actually reduce your team size. But the larger your team is, the more you can benefit from a low code, no code approach, because as you adopt a model-based design approach, one, modularity is much more an integral part of a model-based design tool. For example, you can have a Simulink subsystem, or in Altia, you can have a class that you build separately from other people. So each individual contributor could be working on different parts of the design. The other huge advantage of model-based design with large teams is that the design itself and the implementation itself is also the documentation of the design. It's easy to visually see in modeling tools how one device or widget or piece of the project connects to another device or widget or piece of the project. So really this can help you, even if you have a very large team, it will make the communication across that large team more efficient. And so you don't have check-ins of code that conflict with another person's check-ins of code because they didn't understand how the two of them were interfacing.
Great explanation. Thank you so much for this one.
You're welcome.
I'm gonna have a look on other questions coming in. There's one. Is it better for my platform to say the same and tool to change, or to keep the tools and change the platform?
Well, typically, if you're going to stay on the same platform, there's usually not a lot of need to change your tools unless you want to adopt a more efficient development process, like moving to a model-based design process, which would mean that you would want to change your tools while remaining on the same hardware platform. But once you've adopted a platform like that, you may want to change your hardware platforms and operating systems because of market demands. What we see in the automotive market most of the time is that hardware and OS changes are not necessarily done because somebody decides, oh, I'd like to try this other OS or this other hardware. They're done either because market demands drive that, saying, you must implement a new functionality that's not supported by your old hardware, therefore you need to change. Or, like right now, you can't get the hardware that you were on anymore because of some of the supply shortages. And so therefore it's necessary to continue to production to move to a different hardware platform. If you do have to move hardware platforms, you benefit greatly by having a tool chain and a development process that is the same on those two hardware platforms, because then basically you have a small part of your team, perhaps your hardware engineers and some of the low-level C code, OS level engineers that we talked about, have to make that change. But you don't have to redo the designs, and you don't have to have all your designers, systems engineers, and app level software engineers learn a new tool paradigm.
Brilliant. This gives like a really good answer, and I think it clears all of the question and clarifies all.
Okay.
And one I have left so far, so I would get along with this. Is it realistic that non-engineers can contribute to low-code, no-code environment? And how long does it take for someone to reasonably contribute there?
That's a great question. And the answer is yes, it is reasonable. We've actually seen a number of folks that are non-engineers adopt at least the model-based GUI implementation in Altia design, to where they have actually implemented in an entire system that automatically generates the code for the device. And then on the logic side, we've also seen that, people, and I would say it's not necessarily non-engineers that would do this, but maybe engineers that are more familiar with the parts of the system that they're working on. So for example, you might have, as I said, your systems engineers who are familiar with how the overall system should behave and connect with other systems in the vehicle. They can be in there designing some of that logic in a model-based tool because they don't need to worry about how do I declare a variable that holds this thing. They really just need to worry about this data connects with this data, and they model that in a visual method without having to be code experts. So similarly, you can have mechanical engineers that might be very familiar with, for example, braking systems. They can be doing the braking algorithms in a model-based tool, again, because they don't have to be code experts to do that, but they're braking experts. So they know how the braking system should work. So it does allow both non-engineers to come in and start contributing. And it also allows other engineering disciplines that maybe couldn't write lines of code to implement it to still provide implementation input directly into the model. How long does it take? That can vary a little bit depending on the person's background and familiarity. We have seen people that have really, we can speak with great experience from our tooling, but maybe less for other tools. But from our tooling, we've seen people with no experience whatsoever be able to come in and build meaningful HMI designs in simply a matter of weeks or days.
Sorry.
So it can be very fast, again, because it's intuitive and visual.
Awesome, Jeff. Sorry for interrupting you at the moment.
No problem.
We have in the chat one more question I would like to ask you. Does Altia allow for design reusability, like similar design for different models? What could save time for us too?
For sure. So Altia does allow for a number of design reuse methodologies, from the fact that really any design that you save can actually be imported to another design as a piece of a design. And then we have more advanced things like classing, where you can specify a thing that you instance across your design, meaning that you can build yourself component libraries or even full widget libraries that have all kinds of functionalities to them, and then reuse them across the board. Our automotive customers have done that in a number of situations where they may build, I'm just going to say a branded look and feel clock that they want, and they want that across all of their vehicle lines. So they actually use that same component with the same graphics across various different, from their high end to their lower end vehicles, giving them a very consistent look and feel across their whole line.
Thank you, Jeff, for answering this question as well. I just gonna have another look in the chat if something's popping up.
Okay.
For the moment, it looks good. Everything clarified. Thanks for the great explanations and answers to the questions. So thank you for your presentation, Jeff. Some last words from your side?
So yeah, I'd like to say thank you everybody for joining, and I hope that there was some interesting content in here. And of course, if you do have any more questions or want some more detailed information about any of the things we've discussed today, please contact us. You can use the info@altia.com address down there, and we can get your questions to the appropriate person to get you answers.
Thanks a lot, Jeff. Thanks again for your presentation and everything. And thanks for everyone for joining us today. So I hope to see you soon at one of our next events. And I hope you have a great day.
Thank you, everyone. Bye-bye.
Bye-bye.